let's apply the Newton's second law in that angular momentum form to solve for the equations of motion of a system. And so that expression was the time derivative as observed in the inertial reference frame of the angular momentum of mass p with respect to O as observed in the inertial reference frame is equal to the moment of p with respect to O. And so we need to calculate the left-hand side, we need to calculate the right-hand side. This is the same setup that we had for the earlier example, so we already know that the angular momentum of point P with relative to point O as observed in the inertial reference frame is equal to the mass of point P L squared theta dot, and this is in the EZ direction. And so to finish out the left-hand side, we need to take the time derivative of this quantity, P with respect to O, as observed in the inertial reference frame. And then when we take the time derivative of this, we simply get our constant mass, our constant length, squared. And then when we take the time derivative of theta dot, we get theta double dot, and that's in the EZ direction. And so our left-hand side is complete in this expression. So now we need to calculate the right-hand side. The right-hand side being the moment of the forces acting on point P relative to point O. So for our moment, let's say that P with respect to O, our moment is equal to R of P with respect to O crossed with the forces acting on that particle P, and so that's our moment. And so when we fill this out, M of P with respect to O, our moment, is equal to L in the ER direction, and then this is going to be crossed with all those forces. But we don't have our forces yet. To get our forces, we simply need to draw our free body diagram. So for our free body diagram of this simple pendulum, which we've drawn before many times, it's gravity pointing down, but this is in the not negative direction, but it's in the positive E1 direction. And then we need to add a normal force, and our normal force is going to be pulling on that object, or pulling on the mass, and so this is a minus in the ER direction when pointed back toward O, so from point P to point O. And so let's finish our expression for our moment, where we have L in the ER direction crossed with, it's going to be all these forces, which when we put these in here, negative in the ER direction, plus mg in the E1 direction. Once again, we have the problem in which we have a mixed use of our basis, because ER is in the polar frame, ER is in the polar frame, and then E1 is in the Cartesian frame, in the inertial frame. And so, because we have this information that relates the two frames together, let's take our basis vectors in the inertial frame and convert them to the polar frame. And so that's only one vector, in which we have E1, which is equal to cosine theta ER minus sine theta E theta. Let's make that substitution and expand our cross product. And so we get the moment of P relative to O is equal to L ER cross with, and so negative in the ER direction plus mg cosine theta ER minus mg sine theta in the E theta direction. And so when we distribute our cross products, we get that L in the ER direction cross with minus N in the ER direction is going to be 0, L in the ER direction cross with mg cosine theta in the ER direction is going to be 0, because ER cross ER is equal to 0. And so the only term that comes out of this that we keep is going to be L multiplied times mg sine theta, and this is ER cross with E theta, and so we keep our negative sign from the negative mg sine theta on the right hand side here. ER cross with E theta gives us EZ, and so now we have the moment that would be on the right hand side. And so now that we've got this, we take these two expressions and then we combine our sides. And so let's equate both sides. And so on our left hand side, it's the mass of particle P times L squared times theta double dot in the EZ direction. And then this is equal to negative L mg sine theta, and that's in the positive EZ direction. And so we take our scalars out, we solve for theta double dot, and so we solve for theta double dot, we get the expression theta double dot is equal to minus g over L sine theta. Now, this is a particularly important result because what we've done is we've solved for this simple pendulum. We've gotten an equation of motion that we're familiar with. We recognize this theta double dot is equal to negative g over L sine theta. But notice what we did. We used this form of angular momentum, time derivative of angular momentum is equal to the moment, which is simply just another way of writing F equals ma. F equals ma is buried in this. We can calculate the equations of motion. But more importantly, look at what we had to use and what we didn't have to use here. Notice that in this we only got one equation. In the past, oftentimes what we've gotten is we've gotten two equations where we get an equation that's an equation of motion and the other that's a constraint equation. Because of the way that we set this up, our normal vector was our normal force vector was going through the point in which we were calculating our angular momentum, or our time derivative of angular momentum. And so as a result, we completely eliminated the constraint force. We didn't need it. So that was actually a pretty quick process. That's a great result. However, the bad part about this is that we don't have a constraint force. We don't have an expression for that. We'll have to get that some other way. So it's kind of good and bad. But in addition to that, the other great thing that comes from this is notice that we used F equals ma. We used the Newton's second law, but in our calculations, we only had to calculate the inertial velocity to solve this problem. We never, not once, had to calculate the inertial acceleration. Because if we look back at when we calculated the angular momentum of point P with respect to O, it's all based on a position vector and a velocity vector to be able to get this expression, the mass of point P multiplied times L squared times theta dot. So no acceleration there. And then when we plug all this in, take the time derivative, we simply have to take the time derivative of this expression, which is not acceleration, and then find our moment. So we never really had to calculate acceleration in this example, which is actually kind of lends itself to some of the more advanced methods that you would see in graduate school, where we're calculating using Lagrange's methods or Hamiltonians. We never ever have to calculate acceleration. So that's really a nice finding. We can get this equation of motion, one, by ignoring constraint forces because they didn't show up in our formulation here, but then also we never had to calculate anything beyond the inertial velocity of that particle. And so that wraps up our idea of angular momentum about an inertially fixed point. In lesson 14, we're going to introduce the angular momentum about a point that's not inertially fixed. So angular momentum about a point that's moving, and this expands the usefulness of this equation of angular momentum, or of calculating equations of motion using this form. All right, I'll see you in class.